Welcome back to Talk Tensors, where we dig into the latest and greatest machine learning research. And today, well, we're taking a deep dive into a paper that's tackling a really critical challenge in the world of autonomous vehicles.
Yeah, that's right. For a self-driving car to really navigate our complex world safely, it doesn't just need to see what's around it.
It needs to actually understand, like have a mental map of the roads and everything around it, right?
Precisely. It needs to build a high-definition map, an HD map of its surroundings, but doing that in real time, like while the car is driving, well, it presents some real challenges.
Absolutely. And that's exactly where this paper comes in. It's called FastMap. Fast Query's initialization-based vectorized HD map reconstruction framework. Kind of mouthful, but trust me, the research behind it is really fascinating, especially if you're, into the intersection of AI and the physical world like we are.
Yeah, definitely. Now, existing methods for creating these online HD maps, especially those based on this architecture called DETR, well, they often rely on pretty complex, deep neural networks with multiple decoder layers.
Okay, so you're saying like these models can be really big and resource intensive.
Yeah, exactly. While they can achieve impressive accuracy, they also demand a huge amount of computational power. Think of it like trying to solve a jigsaw puzzle, but instead of trying a few pieces at a time, you're trying every single piece in every possible location all at once until something clicks. You'll eventually get there, but it's not exactly the most efficient way to go about it.
Right. And efficiency is everything when we're talking about autonomous vehicles, right?
No.
You can't have these cars taking forever to process information. They need to react in real time.
Exactly. And that's one of the key issues this paper is trying to address. It points out that these DETR-style frameworks, like MapTR, for instance, they typically start with a set of randomly generated Squishy vectors and then refine them over and over again through these multiple decoder layers, sometimes 6 or more.
So they're basically starting with a bunch of random guesses and then trying to hone in on the right answer through brute force.
Yeah, kind of. Now, while this iterative refinement does help the model understand the data, it also significantly increases the model size and the computational resources needed, which is a major drawback when you're trying to, deploy this technology in a car with limited processing power. It's not like you can just stick a whole data center in the trunk, right?
Right. So that's one problem. But there's another subtle but important issue the paper brings up, right?
Yeah, the standard way of training these models often forces the predicted map points to, perfectly match the manually labeled ground truth points.
Like trying to get a pixel perfect match.
Yeah, basically. Now, while it might seem intuitive to say, the model should predict a point exactly where we annotated it, the researchers argue that this can be too restrictive,
Yeah.
In the real world, sensor data is always going to be a bit noisy, and insisting on this perfect point-to-point alignment, well, it might actually prevent the model from learning the true underlying geometric structure of things like road elements, especially when you have uniform road surfaces and stuff.
Okay, so we've got the problem laid out. Current online HD map reconstruction methods can be, a bit sluggish and perhaps too rigid in how they learn. So then comes FastMap, proposing a more streamlined solution. And as the title suggests, it's all about fast query initialization, right?
Exactly. Instead of those randomly generated queries, FastMap uses a single-layer, 2-stage transformer decoder along with a heat map-guided query generation module. It's like, giving an artist a rough sketch of what they need to paint rather than just handing them a blank canvas and saying, go for it.
Right. A little guidance can go a long way. And to overcome the limitations of point-to-point loss, they've introduced a geometry-constrained point-to-line loss. Right?
Yeah. Instead of penalizing those tiny deviations from the annotated points, it focuses on minimizing the distance to the overall ground truth curve of the road element. It's like giving the model a little more breathing room to learn the shapes and connections rather than obsessing over individual points.
Okay, so the big question now is, how does FastMap actually achieve this boost in speed and efficiency without, sacrificing accuracy? How does this heat map magic work in practice? And how does switching from point to point to this point-to-line loss actually change what the model learns? Let's get into the nitty-gritty of the architecture.
All right. So the FastMap framework, it's designed as an end-to-end system. It starts with input from multiple cameras, like you'd have on a self-driving car. Those images are then processed by a backbone network. Think of this as the initial visual processing stage, extracting features, understanding the basic elements in the images.
Right, like figuring out where the edges are and what might be a car versus a tree, that sort of thing.
Exactly. And then these multi-view features are transformed into a bird's eye view, or BEV representation.
So it's like taking all those camera perspectives and stitching them together into a single overhead view, right?
Yeah, like you're looking down at the car from above. And this BEV view is super important because it gives you this unified perspective of the whole scene, making it way easier to understand the spatial relationships between objects and the overall layout of the road. This BEV feature map then becomes the input to the heart of FastMap, which is the two-stage decoder.
All right, the two-stage decoder, let's break that down. The first stage is all about that heat map guided query generation, right? So instead of starting with random queries, FastMap uses a more intelligent approach. How do they actually create these heat maps?
Okay, so they create these multi-category aware instance heat map ground truths. Basically, for each type of map element the model needs to predict, things like lane dividers, crosswalks, road boundaries, they create a target heat map. They take the manually annotated points and the lines connecting them and represent those in a discrete grid within the BV space.
Okay, so they're basically discretizing the ground truth map information. Then what?
Then they apply a Gaussian kernel to these representations. Think of it like blurring or spreading out the signal around those ground truth points and lines. So in the heat map, you get these fuzzy regions that basically indicate the likely presence of each type of map element.
So like a probability map showing where the model should be looking for these different features.
Exactly. This heat map acts as a spatial prior, guiding the model's attention to the most probable locations.
Okay, so we've got the heat map highlighting potential object categories and locations. But how do we go from that to actual query vectors? That's where the circular sampling method comes in, right?
Yeah, the CSM. To generate these initial geometric cues, they divide the BEV plane into 3 concentric circular regions, like rings around the car.
Okay, like a bullseye pattern.
Yeah, exactly. The idea is that if you sample potential map locations uniformly across the whole BEV space, you might miss those smaller or more distant objects, things that might only appear as a few pixels.
Right, because they would get kind of lost in the noise.
Exactly. So they use this progressive sampling strategy. The outermost ring, L3, is sampled more densely than the innermost ring, L1. The paper gives the specific sampling ratios, which are proportional to the area of each ring. And this ensures you get a more balanced representation of potential map instances, even those that are further away from the ego vehicle.
That's pretty clever. So the heat map tells you what to look for, and the CSM tells you where to look. But how do we actually extract the initial query features from this information?
That's where the coarse-grained cross-attention module comes in, CGCA. It takes those sparse sampling points from the CSM and uses them to gather initial information from the BEV features. It does this through a cross-attention operation, allowing those sampling points to basically look at the surrounding features in the BEV map.
So it's like each sampling point is scanning its neighborhood for clues.
Yeah. The paper gives us the formulas for the key positions and key features used in this cross-attention. The key positions are a learned transformation of the sampled coordinates, while the key features combine the sampled BEV features with the category information from the heat map. And the output of the CGCA module is a set of coarse-grained map embeddings. These are feature vectors that have a preliminary understanding of the approximate location and semantic category of potential map elements.
Okay, so we've got these initial rough drafts of the map features. Mm-hmm. What happens in the second stage with the fine-grained cross-attention, the FGCA?
So in the second stage, we're refining those coarse-grained features and filling in the missing details. It enables a deeper interaction between those coarse features and the complete BEV features. The coarse features are passed through a multi-layer perceptron, an MLP, to generate these fine-grained query coordinates and reference point offsets.
So it's like taking those initial sketches and figuring out where to add the finer detail.
Yeah, exactly. Then they use multi-scale deformable attention. The full BEV features act as the key and value, and those generated query coordinates and reference points guide the attention mechanism to focus on specific regions within the BEV map. This allows the model to extract fine-grained instance features that contain more complete geometric and semantic information. The paper again provides the specific formulas for these query positions, reference points, and the resulting fine-grained instance features.
Okay, so two stages. First, a rough localization, then a focus refinement. That makes a lot of sense. Now let's talk about the loss function, because the shift from point to point to point to line seems like a pretty big deal.
Yeah, it's a key innovation in FastMap. The loss mechanism is designed to avoid those limitations of forcing a perfect match between predictions and annotations. It has several components. First, there's the points loss, or LPP. This is specifically used for the start and end points of open map elements, like lane dividers.
Okay, so things that have a clear beginning and end.
Exactly. It calculates the L1 distance between the predicted and ground truth start and end points, and this helps constrain the overall length of the predicted map instance. Importantly, they don't apply this LPP loss to closed elements like pedestrian crossings, which don't have those distinct start and end points.
Right, because those are continuous loops. So LPP handles the overall length. What about the points line loss, the LPL? This is where the geometry constrained supervision really comes into play, right?
Yeah, the LPL measures the perpendicular distance from each predicted point, excluding those endpoints handled by LPP, to the line segment defined by two consecutive ground truth points that form the curve of the map element. By minimizing this distance, the model learns to align its predictions with the overall shape of the curve, rather than being penalized for small deviations from those individual annotated points.
It's like saying, hey, you don't need to hit every nail on the head, just make sure the overall shape of the fence is correct.
Exactly. And this elegantly addresses the issue of feature similarity between closely spaced points and the potential redundancy caused by that strict point-to-point matching.
Okay, that's a much more intuitive and flexible way to guide the learning process. There's also an auxiliary line loss, the LOL. What does that do?
The lull acts as an additional constraint to prevent the predicted points from, going astray. It calculates the sum of the distances from a predicted point to the two endpoints of its corresponding ground truth line segment. By minimizing this, the model is encouraged to stay within the boundaries of the ground truth segment and not wander off onto some imaginary extension of that line.
Keeps things nice and tidy.
Yeah.
And then, of course, we have the heat map itself. There's a heat map loss, the L focal involved as well.
Right. They use a focal loss on the predicted heat map to make sure the model is accurately identifying the presence and location of those map elements within the BEV features. And what's particularly interesting here is the inclusion of a Gaussian heat map weight, WGauss. This weight increases as you move away from the center of the heat map outwards.
So it's giving more importance to those predictions further away from the car.
Yeah, it's basically saying, hey, pay attention to those distant objects too, they're important. The formula for this WGauss includes parameters that control how quickly this weight increases with distance and the overall spread of the Gaussian.
Okay, and finally, we combine all these individual losses into a total loss, the L total.
Right. The total loss is a weighted sum of the losses from both decoder stages, including a loss on those reference points generated in the first stage, and the heat map loss. The paper gives the specific weights they use for each loss component in their experiments, which were determined through careful tuning to get the best overall performance.
Right, so that's a FastMap framework in all its glory.
Yeah.
Now, the million-dollar question, how well does it actually work? They tested it on the new scenes in Argoverse 2 datasets, which are pretty standard benchmarks for this kind of research. What did they find?
Well, the results are pretty impressive. On new scenes, FastMap Tiny, which is the lightweight version using Resna 18 backbone, it significantly outperformed the baseline MapTR method in both mean average precision, or MAP, which is a key metric for object detection accuracy, and frames per second, or FPS, which measures inference speed.
So it's more accurate and faster. That's a win-win.
Yeah, exactly. And FastMap base, using a more powerful ResNet 50 backbone, it further improved the FPS with a slight increase in MAP compared to a more recent baseline, MapTR v2. And get this, FastMap Large achieved state-of-the-art MAP on new scenes, proving that this efficient heat map initialization doesn't sacrifice the model's ultimate accuracy. They also saw bigger improvements in those stricter evaluation ranges, which means it's making more precise predictions when it really matters.
That's awesome. What about Argoverse 2? That one's known to be quite a bit tougher because of its more complex and diverse urban environments.
And the good news is the trends from new scenes held true on Argoverse 2 as well. Across all the FastMap variants, they saw consistent improvements in MAP compared to the baselines. This suggests that the architecture is pretty robust and can handle various real-world driving scenarios.
Okay, so it's not just a one-trick pony. They also did an ablation study, right?
Yeah.
Which is always important for understanding the contribution of each individual component. What did that tell us about FastMap?
The ablation study really highlighted how effective the different modules are. Adding the CGCA, the coarse-grained cross-attention, led to a significant jump in MAP, showing how important that informed query initialization strategy is. The FastMap loss function, with its point-to-line and auxiliary components, also contributed significantly to the gains. And the circular sampling method and the Gaussian heat map weight, they further boosted the results, showing their role in helping the model detect those more distant elements.
So every piece of the puzzle is doing its part. And what about the efficiency aspect? Did they deliver on the promise of faster inference?
Oh, absolutely. They compared the inference speed and parameter count of FastMap Tiny to different MapTR configurations with varying decoder layers. FastMap Tiny was much faster with a similar or even smaller number of parameters than MapTR, even those with fewer decoder layers. And FastMap Base converged faster during training compared to MapTR v2, achieving a much higher MAP in the early stages of training.
So it's not just about the final performance, but also how quickly it gets there.
Exactly.
They also briefly mentioned evaluation using metrics like ACD, ARD, and AJP. What do those tell us?
Those metrics, the average chamfer distance, average radian distance, and average jitter points, they give us a more detailed look at the geometric accuracy and smoothness of the predicted map vectors. Lower values are better, and FastMap generally scored lower across these metrics, suggesting of its predictions are not only more accurate, but also smoother and more consistent.
So no weird wobbly lines or anything like that?
Yeah. Nope. Nice and smooth. And the visualizations in the paper also support this. You see accurate heat map predictions, even in complex intersections, and smoother, more complete vector outputs compared to the baselines.
Okay, so to sum it all up, FastMap tackles that efficiency problem in online HD map reconstruction by introducing this single-layer, two-stage decoder with a really innovative heat map-guided query initialization method. It also uses a more flexible and geometrically aware point-to-line loss, and the results across multiple datasets show that this leads to significantly faster inference, faster convergence, and state-of-the-art or highly competitive accuracy. This is a big deal for deploying autonomous vehicles, especially when computational resources are limited.
Definitely. Being able to generate those high-quality maps on the fly without needing a supercomputer is crucial for making autonomous driving a reality. And as the author suggests, this improvement in map reconstruction can also benefit downstream tasks like motion prediction and planning.
All right, now for our Novel Notions segment where we speculate on the future directions inspired by this research. So, given what FastMap has achieved, what other interesting research avenues could this open up?
Well, building on this whole heat map guided query initialization idea, one intriguing direction could be to explore its application in other perception tasks beyond HD map reconstruction. Like, think about 3D object detection in crowded urban environments where there's a lot of occlusion.
So like when cars and pedestrians are all bunched up together and it's hard to see everything clearly.
Exactly. Could we use, category-specific heat maps, maybe leveraging contextual information or even temporal data from previous frames to guide the initial placement of 3D bounding box proposals?
It's like giving the model a heads up on where to look for those hidden objects.
Yeah, it could potentially lead to more robust and efficient 3D perception, maybe even with simply detector architectures.
That's a cool idea. What else?
Another thought is to further develop and generalize this geometry-constrained point-to-line loss concept. Apply it to other structured prediction tasks, like predicting the trajectories of multiple interacting agents.
So instead of just predicting individual points, we could focus on predicting the overall flow of movement.
Yeah, maybe even explore a kind of tubular loss where the predicted trajectory is encouraged to stay within a certain learned geometric corridor. This could lead to more realistic and less brittle trajectory predictions, especially in those tricky situations with lots of uncertainty.
It's like saying, we know the general direction things are going, but we don't need to predict every single step along the way.
Exactly. And this could even have implications for explainable AI in autonomous systems where the predicted behavior is more than just a sequence of coordinates.
Right. It's about understanding the underlying principles of movement and interaction. Some really thought-provoking stuff.
For sure.
And for those of you who want to dive deeper into the specifics, we've included a link to the full FastMap paper in the show notes. is a must-read for anyone interested in the cutting edge of autonomous perception and machine learning for spatial understanding.
Absolutely.
Well, that wraps up our deep dive into FastMap. Thanks for joining us on Talk Tensors. We'll catch you next time.